Hi, I am Ricardo Soares. I'm a doctoral student at Federal University of Rio de Janeiro, and I'll present the work Laminar Coflowing jet flame side tubes with regular walls. Introduction and motivation. Diffusion flames play an important role in many practical combustion applications. Although in these applications are usually subject to turbulent flow, laminar diffusion flames provide the basic component for Laminar model, in which the structure of turbulent diffusion flames are interpreted as a composition of a set of laminar flames. Most studies of diffusion flames in the presence of regular walls are related to flame holders, for which, for which the solid wall is located downstream of the flame. And in the flame holders, flame wall interaction, for example, is a field of combustion that has not been investigated yet with sufficient care. So the objective of the present work is evaluate the interaction of the wall regularity and the reactive flow. A parametric study is conducted to evaluate the effects on the recirculation zones and the flame shape of the position and the size of the regularity, of buoyancy, and of the Reynolds number of the fluid flow. Mathematical model. A sketch of the physical domain is shown in figure 1. Based on the physical domain, the reactive flow governing equations are written in the cylindrical axiomatic coordinate system as continuity equation, axial momentum conservation equation, radial momentum conservation equation, and mixed refraction conservation equation. This last equation comes from the linear combination of the chemical species and the energy equation in order to eliminate the reaction terms. The governing equations were written under some assumptions. Firstly, thin flame hypothesis considered. Also, the heat flux due to radiation effects neglected. To further simplify the governing equations, it is assumed that dissipation by viscous stress and the flow work is negligible, as well as the Surrey and the full effects. Besides, the specific heat is considered constant for all chemical species, and the diffusion velocity obeys the Fick's law. In this model, the chemical reaction described by a single one-step irreversible reaction, corresponding in an infinitely fast conservation of reactants into stable products. Denoting the variables at the flame surface with the subscript f, it can be shown that the mixed refraction at the flame can be given by the following equation. With the formulation for the mixed refraction, it is possible to obtain the temperature profile and the max fraction of the chemical species from the solutions of the governing equations on the fuel side of the flame and the oxidizer side of the flame. The thermophysical the temperature variation of the thermophysical properties and transport coefficient is given by the following expression. Also, the heat generation parameter is given by an estimated value for the flame experimental temperature according to the following equation. The governing equations are subject to the following boundary conditions: symmetry around the center axis, fully developed condition along the outlet of the solution domain, uniform inlet velocity and mass fraction profiles, non-slip condition, and impenetrability condition at the inner wall of the arrow tube. A Gaussian function models the wave wall as the following equation, where h is the axial position of the wave wall peak, p controls its radial position, sigma controls the width of the wave wall, and the initial condition is given by the following expression that corresponds to static isothermal oxidized only conditions. A Fortran code was developed in order to obtain the numerical results. The finite volume method was used to discretize the governing equation with a collocated grid arrangement, and the weighted upstream difference scheme interpolation is used in a structure mesh. Grid is numerically generated by the solution of a partial differential equation. The simplex algorithm is employed to address the pressure velocity coupling. Initially, a grid conversion study was conducted considering the limited case without regularity. The streamline and temperature profiles obtained for free meshes were compared, and according to the gains on the result in relation to the simulation computational time, an intermediate size grid was selected for a present study. Besides the grid conversion study, code validation using numerical and experimental liter data was also performed. Results showed that we cannot reproduce the experimental results in their entirety behavior. However, the model can estimate the temperature field, the flame position, and its height, and the molar fraction of the chemical species in a complete combustion of a hydrocarbon in a satisfactory way. The detailed validation procedure and its results are shown later on and Sauer. Results. In order to explore the results, a base case is initially established. The base case operational conditions are shown in Table 1. Figure 3 shows the difference in the temperature field, streamlines, and flame shape between the case and the case with limit without irregularities. For better visualization, the results are plotted for a complete section of the burner, although the governing equations are solved in axiomatic domain. The flame presents an overventilated behavior for both cases. For the base case in Figure 3a, immediately upstream the irregular wall peak, the oxidant-rich flow deflects in the centerline direction, deforming the flame and decreasing flame height, when compared to the case without a regular wall. This reduction in the flame height is related to the improvement in oxidant transport due to the enhanced convective effects by the regular wall for the base case. Besides the change in the radial velocity that affects the flame upstream the regular wall, the regularity peak, an increase of the axial velocity along the center line is also observed, due to a reduction in the transversal area imposed by the regular wall. An increase in the recirculation zone downstream of the regular wall peak is also observed due to the wall regularity that induced the flow separation. The influence of the number of the peak was also studied through simulations considering two undulations in the regular wall. The inclusion of more undulation peaks were compared to the base case in Figure 3a, generate new recirculation zones downstream of the undulations. Flame shape is affected upstream of the peak of each undulation as oxidant is deflected toward the channel centerline. In Figure 4 shows a stronger flame deflection connected with the regular surface peak closer to injection than the deflection in a high axial position. In order to evaluate the buoyancy effects on the flame and flow field parameters shown in Figure 5, zero gravity acceleration simulations were conducted for the cases shown in Figure 3. Gravitational effects are responsible for the entry of cold external air near the solid wall, generating or intensifying recirculation zones, a characteristic that can be observed comparing Figure 3b with Figure 5b. Thus, in the absence of gravitational effects, the overventilated flame width increases for the Heffered case with and without irregularity, as shown in Figure 5. The influence of the irregularity position was also investigated through changes in the parameter h. For the case in Figure 6a, the flame height is 7% lower than the base case shown in Figure 3a. The flame deflection occurs in a lower axial position associated with the oxidant deflection. The recirculation zone is formed in a lower axial position due to the regularity new position which induces the flow separation close to the injection surface. For the case in Figure 6b, the flame height is 3% higher than the base case in Figure 3a. Two recirculation zones are observed for this regularity position, one upstream of the regularity caused by the buoyancy effects and another one downstream of the regularity caused by both buoyancy effects and solid wall shape that induce the fluid flow separation downstream of the peak of the regular wall. The irregularity high effect was also investigated changing the parameter p. The results are shown in Figure 7. For the case in Figure 7a, it's verified that the flame reached an intermediate height around 9.2 centimeters. This value is between the value obtained in the base case in figure 3a than the case without regularity in figure 3b. Decreasing the regularity size reduces the reflection of the oxidant-rich stream flow towards the domain centerline direction, leading an increase in the flame height. For the case with for the case in the figure 7b, it is observed an opposite trend. Increase the regularity size, it is raised the deflection of the oxidant-rich flow toward the centerline direction, decreasing the flame height for a fixed regularity position. Finally, the effect of the Reynolds number is investigated by changing the oxidant axial inlet velocity. Two values of Reynolds number were tested. Reynolds equal to 500 and Reynolds equal to 150. Increase the Reynolds number of the flow in figure 8. The oxidant flow increases, providing a larger amount of oxidant, forcing the flame surface to achieve a smaller height when compared to the similar case with the original Reynolds number in figure 6b. Compared the temperature field in figure 6b and figure 8a, we observe that a large amount of oxidant entering a low temperature affect the temperature throughout the entire domain, decreasing it in a fixed axial position. This large amount of oxidant also changes the convection intensity, modifying the position of the recirculation zone downstream of the regularity position, which is formed in a high axial position. The area of the recirculation zone is also modified, caused by the fluid flow separation induced by the regular wall shape itself. The recirculation zone becomes much more less intense with a bigger area extrapolating the solution domain. Decreasing the Reynolds number of the fluid flow in figure 8b, the oxidant flow rate is decreased, so the amount of the oxidant will be insufficient for complete combustion of the fuel. The flame presents an underventilated behavior, expanded into the solid walls. In this case, two recirculating zones are formed, one upstream of the regularity caused by the buoyancy effect and another one of the regularity caused by the solid wall shape that induces the fluid flow separation downstream of the peak of the regular wall. Conclusions. The regularity, affect the flame shape inside the tube. Increase the regularity maximum height or position the regularity close to the reagent inlets, the over-ventilated flame height decrease. Also, gravitational effects are shown to narrow and to stretch the flame. Recirculation zones are formed near the reagent inlets due to buoyancy effects and just downstream of the regularity caused by solid wall shape that induce the fluid flow separation. In some cases, these two recirculation zones are shown to coalesce into a single flow structure. The variation in the Reynolds number of the flow affects directly in the temperature field in the recirculation zones position in circulation zone positions and in the flame behavior. Reference used in this presentation.